Hi everyone. Hello. Hello. Can you hear me? Cool. So sorry if my voice is a bit hoarse. I'm still recovering from a cold last week. So anyway, I'm going to talk about how to scale observability without bankrupting the company. And the reason I chose this topic is because I think a lot of people, this was actually mentioned yesterday in Joe's talk, are dealing with this tsunami wave of observability data. But we're all under pressure to keep those costs down, especially in this current environment. And so I figured I'd share some of the ideas that we've already done on how we've controlled costs at Netflix at our scale, but also talk about some of the ideas that we are working on to solve this problem going forward. So just a bit about me. I've been a serial founder. I built and sold a couple of enterprise SaaS companies. The last one was called Dataloop.io, if any of you guys remember that. We actually launched at Monitorama in 2014, so that was my first time coming here. And it was an observability startup competing with things like Datadog and all those cloud monitoring tools back in the day. And my other claim to fame is I actually built DevOps Exchange. It's the world's largest DevOps meetup, about 12,000 members worldwide. So if you're in London, San Francisco, or any of the other cities it operates in, check it out. And after we sold the company in 2019, I took a year off, and then Netflix, which used to be one of my largest customers, approached me to basically head up the telemetry engineering team, which is how I ended up at Netflix for the last 3 years. And then my other kind of claim to fame, which I'm quite proud of, against my marketing team's wishes, we did this campaign at Monitorama 2016 when it was still funny to make that kind of joke about make monitoring great again. In November it wasn't so funny, but it worked in July. Anyway, so what do we do at telemetry engineering? So the team that I run, we have 9 engineers in total. We essentially are responsible for all the collection and agents and storage, processing, and query of all our observability data across the company. So you can imagine that's quite a big scale. And we provide all the APIs and everything for our alert services to sit on top of it, and all our UIs and everything internally. So all our observability products basically rely on us to provide the data so they can see what's going on with their systems. And we have to do that. This is our charter at the bottom. We have to do this in a performant, reliable, and cost-effective way. So what kind of scale do we operate at? Well, as you can imagine, we're a global online company, so we have quite an immense scale. So on average, we're doing about 17 billion metrics a day with about 2-week retention in hot tier. We're doing about 1.5 petabytes of logs a day, again with 2 to 6 months retention, depending on the different apps that we're collecting logs from. And then with tracing, we're storing about 700 billion trace spans a day with 2-week retention in the hot tier. Which is a very heavily sampled number, so definitely not all the tracing that we would like to collect. So as you can imagine, there's petabytes of data coming into our systems every day, and we have to store it for 2 weeks in hot tier, and then we use S3 for longer term storage. But one of the things that we've been pretty good at is we've actually done a really good job of controlling our costs. Now these scales are not, not equivalent. So even though that number's halfway to the metrics number, it's not the same. I can't share our costs, but I can at least give you an idea of like how the costs look like as our metrics load went up over the last few years. So you can see as we scaled up to 17 billion metrics, we've actually reduced it a little bit recently. Our costs have been pretty linear and flat. So we haven't really gone up exponentially with the amount of data as a company scaled up. Another way to look at our kind of value to the company, how we earn our salaries, is in December I actually did an exercise to look at like a bunch of vendors and just looked at basically our log monitoring solution. So we do 1.5 petabytes a day. When I went out to market, you can see the tiny little red thing there is how much we actually cost per year. And then those are all the other vendors. None of the vendors could even get in the same ballpark as what we're able to do. And that's actually one of the, this is a constant question we get inside Netflix and externally, is like, why didn't you buy, why are you building all this stuff internally? This is why we build everything, because we can do it way cheaper than what vendors can offer us. Although we are willing to work with vendors who can get us into that ballpark. And Joe talked about kind of monitoring costs, kind of getting out of control yesterday. He made a comment that Roy, one of my predecessors, said that we used to be at 25% in terms of our infrastructure costs for observability. Can anyone hazard a guess if we're above, below? Anyone above 10%? 5 to 10%? Which is a typical range. Below 5%? Okay, so the people who said below 5%, That's pretty much where we are today now. So we went down from 25% of the infrastructure cost. We're now about 4.7% of our infrastructure costs just spent on observability infrastructure. So how do we do it? How do we get to those numbers and make sure that we don't bankrupt the company as the amount of data goes up? So in the beginning, we were quite traditional. So Atlas is about 11 years old. And Atlas is our in-memory time series custom database. You can go into GitHub, it's open source. We basically did what a lot of monitoring tools do, which is we wrote all the data into the time series database, and then for alerting, we'd basically run every 60 seconds a cron job that would go into the query service and query that database to basically check if an alert had triggered or not. So had we continued with this model, it worked when we had thousands of alerts, but when we get to hundreds of thousands of alerts, this started to break because it meant that we basically had load from both sides. Not only did we have to write all this metric volume into the database, we also had to run every 60 seconds more and more queries that just kept hitting the database, and adding load to the thing. And so we would have had to add loads more Atlas nodes just to kind of scale with that load. So we took a different approach. We moved to streaming. And this is, if there's one thing you take from my talk, if you can do stuff in the streaming path, you should always do it in the streaming path. It's way cheaper. It's way, it has a lot of benefits, but it's way cheaper. That's really the key kind of source here. So how do we do it today? We basically stream in all our metrics, logs, traces into ingestion. And now, in real time, our ingestion service forwards on basically all the queries that we need for our alerting system in real time to the alerting service that then does its evaluations and basically triggers the alerts. So not only do we get lower latency, that also has allowed us to scale to millions of alerts today without having to basically add a huge amount of infrastructure to support that. So it's been very cost effective for us. And now we really just use queries just for dashboards and for user queries and things like that. So it reduces the load on the database as well. So how does our streaming architecture work? Well, we didn't go down the route of building it on Kafka. That would have been super expensive because you can imagine as we have this tsunami of data coming in every day, petabytes of data every day, if we had to write that all to disk, manage a huge Kafka cluster, it'd be super expensive and super hard to manage at scale. So actually, we came up with something that's pretty simple. The trade-off being that unlike Kafka, we don't have that resiliency. We could lose some metrics from time to time. However, the amount of time that actually happens is very, very rare. And this gets us significantly cheaper kind of streaming capabilities than we would get on something like Kafka. So how does our streaming service actually work? Well, essentially, we have subscribers. So alerts could be one of our subscribers. Inside, we have this library called an evaluator. As we submit queries from alerts that we're basically evaluating, the evaluator adds it to the query index. And the query index is basically, this is kind of like the bit that, is took a long time to get it really working and right. And essentially what it is basically, it's just a super compact, super fast lookup index. It dedupes like duplicate queries and stuff like that, and basically just enables you to store it in a few hundred megabytes of memory. And the reason we want to do that is because we want to load that in another library called Atlas Registry in all our ingestion services and some of our sidecars as well. And we want to load that index in, and in real time, as every single data point streams in, log, trace, what have you, we want to do a real-time lookup. Does this match any of the queries in my in my index at the moment? And if it does, we forward it on to LWC, which is the name we call our streaming service internally. If it doesn't, we just forward it on to write in the database or storage as normal. In fact, well, everything gets written into the storage, but the only thing that gets forwarded to our LWC service is the stuff that matches stuff in the query index. So what happens when it gets to LWC API? They're really just dumb proxies that have, that when you go back to the beginning of it, where the evaluator library essentially connects to LWC using WebSockets. It says, these are the range of queries that I'm interested in. Please forward me on any data that you receive through WebSockets. And so essentially, the ingester matches against all the data, it pushes it into LWC, and then LWC then pushes it into the evaluator, then does a final calculation to create the graph or what have you in the subscriber. So it's a very cost-efficient way of doing it. And all of this is open source, by the way, so you're welcome to go to our GitHub repo and check out how all that code works for the registry and the library and the evaluator and LWC. But one of the other cool things about it, it enables us to do really high cardinality metric queries very cost effectively. So, we would not want to store, for example, a metric that had request ID on it. That would add billions of metrics to our time series database. But in LWC, you could push something high cardinality, maybe not that high cardinality, but something in that range. And we can also do it at high granularity. So in our time series database, we store everything at 1 minute intervals. You can actually push data at a faster frequency with more cardinality. And because we're doing it in the streaming path, it's actually very cost effective for us to basically do aggregations and filter out all the metrics that we care about using that streaming path. So this is something that we're really excited about. And actually, we added it last quarter to logs and traces. So before we were only using it for metrics. Now we're doing it for all of our logs and tracing as well. So essentially, we made a couple of modifications to it. So we have 2 ways you can basically subscribe to our streaming path. One is I do a select query with rejections where I want you to send me all the traces and logs that match a certain tag or expression or what have you. And again, we can just forward those on as a fire hose for whoever wants to receive those. And with projections, we can even just collapse it down to a few fields that you care about. And then we also can do analysis queries. So, one of the biggest problems that we have at our scale is like, how do you basically do a graph of showing how many errors for a log, appeared on the dashboard or something? That's quite expensive for us to compute, and especially if we had to do it at query time. But in the streaming path, we can actually do that, pretty simply, because as the logs stream in, we can just keep pushing it over to the subscribers, and the subscribers can start building up a graph that can then be streamed onto whichever other service needs it. So we're using it quite extensively for a lot of our data now. So then I get back to build versus buy. So I showed you earlier on logs, we basically do that per year versus all the other solutions that we looked at. And actually internally before that we were using Elastic. And it's fair to say, had we continued on Elastic, we'd probably be one of the bars closer to the end kind of thing, just because of the way it indexes and scales and all that kind of stuff. So so how did we get to this kind of cost profile? So we actually have 2 versions of our log. So this is how we actually started and got this cost down in the first instance. So we actually ended up building a custom solution using S3 and Parquet. And the way it worked is as logs stream in, we have a kind of pipeline that uses Kinesis to pass messages and S3 to pass the data, because you don't want to put the data into Kinesis. But essentially, it would go into the ingester, go to the transformer service that would essentially do all the normalization, clearing up fields, and just basically adding some fingerprinting and other things that we do there. And then the committer would then push it into a service that we built internally, which is open source, called Iceberg, which is basically a catalog on top of Parquet files in S3. And then we'd push everything into S3 and Parquet. So the storage costs went down massively, especially with Parquet compression. We can store petabytes of data on S3 very, very cost effectively. And then with Iceberg, we can catalog them. And then what we had on the query side is we had PrestoDB, which today is called Trino. And essentially, that was a cluster of nodes that would then use Iceberg to look up which Parquet files to basically search during a query, and then would basically go into S3 and essentially do its parallel kind of scans, and then return the results back to the query API. And this works pretty well. I mean, we're still using some of this stuff today. We're still in the migration to the next version I'm going to show you. Some of the issues, though, were, we kind of traded off cost and latency. So, 2 to 3 seconds isn't that bad most of the time, but it is sluggish. So we did have some complaints from users saying that, when they moved to our centralized logging solution, that they would just find some of the queries, especially for large customers that sent a lot of logs, that they were quite slow in some circumstances. The other thing that we had, because of the way Iceberg works, it would take about 3 to 5 minutes for those logs to appear in the storage. So there were some downsides to this approach. So we ended up basically going down a different path, where we started using ClickHouse as a hot tier. And actually, as we added it as a hot tier, we then realized, actually, why don't we just use it for everything? And Uber's actually been using ClickHouse, I think, for all their logging for quite a while now. So it's got a lot of precedent before us. So we're actually in the path of migrating to this architecture, but this is where we're going to be by the end of this year. But essentially, this has actually ended up being cheaper for us overall, because as you can imagine on the previous slide, I had all these other services. So I had Druid, which I forgot to mention, which is like calculating all the metrics and aggregates on top of logs, like how many errors, how many times did we see this field, that kind of stuff, into Druid, so that we can let people dashboard their logs using our dashboarding solution. So we don't have to get rid of that anymore. We can get rid of that because now ClickHouse provides materialized views, aggregates that we can just basically use on top of ClickHouse. We don't need Iceberg, which runs on Hive tables. We don't need a PrestoDB cluster that concurrency has to run, because it's very hard to kind of auto-scale it up and down in real time as queries kind of come and go. So we removed, and we don't need the committer anymore, which writes everything in Parquet. So when you kind of simplify it down, now we can basically push everything within 30 to 45 seconds. It goes into ClickHouse. That becomes our kind of read and write cache on top of S3. And it has S3 support. That's something that he added, I think, in the last year or two. And while we still haven't put all of our data into it for the full 2 weeks that we're trying to do on S3, because once you get into S3, you do get into some latency issues. In general, it's been working really fast, and our query performance has gone really well. So we're big fans of ClickHouse. So that's kind of what we've been doing. And I think, if I was to sum up the kind of 2 big ideas there, it's streaming and using low-cost object storage where we can to basically store this data, the historic data, as cost-effective as we can. So I want to talk a bit now about where we're going. So in terms of our challenges, these are the kind of things that we need to think about when we think about where do we need to take our platform going forwards. We are expanding to more regions on AWS. We also have way more environments that we need to support, things both inside our VPC and outside our VPC. We also have way more use cases. I'm sure some of you are aware we've launched Live this year. We have gaming, we have ads. Like all of these different use cases have different requirements for how they want to store metrics, logs, and traces. And so we've had to become way more flexible for a whole range of use cases. Machine learning is another one. We do a lot of machine learning, AI stuff internally. They have different requirements for observability. So we've had to basically become more flexible to all these different use cases. We have way more scale. Like as we add in all these new services, live, gaming, more members, all this kind of stuff, our data just keeps going up. And that's not going to stop. It's the same for us as everyone. Data just keeps going up, and our users want more cardinality, which to be fair, we've kind of limited their ability to do very high cardinality by telling people they have to switch certain things off and things like that. They want more cardinality so they can dive in more into their metrics and logs and traces and get more kind of insights out of them. And more signals. Like we are really kind of supporting metrics, logs, and traces today, but we are thinking about continuous profiling. We're thinking about, NetFlow monitoring. We're thinking about real-time user monitoring, which I think Cliff was talking about earlier. So, how do we add petabytes more data sets to our existing data sets, in a scalable and cost-effective way? And then we also want a more unified UX, because of the history of our team, a lot of our tools have been kind of, somewhat disjointed and siloed and built by one developer over here and all this kind of stuff. We want our platform to be more unified. And for this kind of use case for telemetry, I want to have the same user experience whether I'm querying the last hour of data or a year ago of data. So I don't want to have a disjointed query experience having to kind of get access to my data and do queries and stuff. And again, like our charter, we have to do this in performant, reliable, and cost-effective way. So this is kind of where we think we're going to take the future of telemetry at Netflix. And we're not the first people to call this term. I think we're probably more advanced in terms of how we're thinking about this. But essentially, we want to build an observability data lake. We want everything to be centrally controlled so that different developers across Netflix do not have to think about setting up their own metric solution or their own logging solution. They can just basically set up their service, forward it to us, and it just works. There's nothing else to do kind of thing. We want it to work at petabyte scale. We want it to work in our own VPC. I think Joe talked about this yesterday. Like one of the reasons we can't use SaaS vendors, it would cost us millions of dollars just to ship the data to a SaaS vendor, let alone pay them 80% margins on top of their more expensive AWS pricing than what we get internally. So it has to run in our own data center. We want to be able to do low query, queries on low latency queries on top of this data, and we want to be able to support a much higher cardinality than we've done before. So we call this the observability data lake because it essentially allows us to put everything into something that we can store it very cheaply, but provide this consistent user experience across the business. The other things we also want to do, we're seeing a lot of demand for business analytics on top of our data. So we want to be able to enable business users to generate business analytics on top of our observability data. So this is why we look at it more of a data lake than just these kind of bespoke solutions for metrics, logs, and traces, and all that kind of stuff. We also would like to do compound queries and alerts where, maybe you can alert triggered off, if the CPU goes up and then my log errors go up, then only send me an alert instead of having these systems kind of all calling from different places. So that's kind of where we're going. And so what I'm going to talk about now is a bunch of the stuff that we are working on, we've been running experiments on. Some of these are quite early. Some of these are things that we're still kind of experimenting on, so I'm not going to say that they're all proven and working yet. But the reason I want to put it out there is because, we're not a vendor. We have nothing to hide. We actually want to work with people in this industry that can bring us great ideas, maybe other vendors, that kind of stuff. So I'm going to put out a bunch of the ideas that we've been thinking about and how we think this could basically be built. In an effort to kind of inspire conversation and maybe have conversations with you. I've already spoken to a few vendors here on how maybe we could work together to kind of bring this to reality. So the biggest problem we've always had in observability is, there's CAP theorem, I call it the CSL theorem. It's always been very hard or nigh impossible to basically do low cost at large scale with low latency. You always have to break one of those if you're kind of doing it. So this is the challenge that we've got to solve, especially with an observability data lake. How do we basically bring these three together in a way that we can do it low cost, at large scale, with low latency? And it turns out, actually, we already actually have a solution for that, which actually does match all those criteria, and it's basically doing it in the streaming path. If we were today just to basically forget about historic data and just essentially allow you to start a query from the browser using our LWC service, and then basically just query that stuff as it came in through ingestion using the streaming stuff that I talked about earlier. We could do very high cardinality, very low latency kind of queries and searches and stuff, in the UI. And so at the core of this, it starts with streaming. But then, at some point, you want to look at historic data. You want to look for not just the data that came in since I started that query, but everything that came before that. Maybe for the last hour, typically it's for the last hour or two, but maybe for the last week, 2 weeks, maybe for the last year, who knows. So how do you sort out historic data? Well, ideally we want to put it into low-cost object storage. And this is where we've got a bit of inspiration from companies like Snowflake. There's a few vendors here that are pitching this now and stuff like that. Like, how can you store observability data at scale on S3? Because the challenge is you have this kind of trade-offs. Yes, we can get it super cheap, like hundreds of K per petabyte, and again, that's assuming no discounts on AWS, plus no compression on Parquet. Parquet is actually quite compression efficient. But essentially, we can go all the way from 280K per petabyte, just with list pricing on AWS, all the way to 69 million if we would store all a petabyte of data in memory. And obviously, we don't want to do it in memory. We do that for metrics, but that's because the metric data set is much smaller than logs and traces. But this EBS one here gets you closer, below 1 million, but that asterisk there kind of tells you that doesn't include the cost of running the instances that have to be attached to the EBS volumes. I didn't bother pricing that in, kind of thing. So this is just the raw cost of having an EBS volume SSD. So ideally, we want to be at that end of, ideally we want to be at that end of the scale. But we have to solve the latency issue. So I think the way we're thinking about it is it really comes down to the catalog and being able to use dynamic compute to basically query that S3 bucket in a very cost-efficient way. So the catalog I'll come back into in a minute. That's basically about reducing fan-outs. But for the lambdas, this is something that we've been experimenting with. Why do I need to have an always-on query cluster? You can use that for like day-to-day queries, but what happens when I want to reduce that query for a very large query that I need more compute for? Well, lambdas scale up pretty fast. There are some issues with it. They have a very small response payload. So Honeycomb did actually a great talk on this. They're using this internally. But one of the things that they do is they basically write the result when the function finished to S3, and then the query engine then goes and pulls it from S3. That adds a few hundred milliseconds. If you're trying to compress your query latencies, you need to do it faster. So it turns out we've already solved this issue again for Atlas. When we do queries, we actually fan out to thousands of Atlas nodes, and then we open a long polling request, which then streams back all that data, and our query service basically builds up the response in real time as the data streams in, so then we can then stream it back to the user. So why don't we apply that to lambdas and other parts of this architecture? Like, there is a way to get lambdas to stream back data as they find rows in the Parquet file, and then just stream back to your query engine, and then maybe you can even stream that to the user. So like in the UI, why do I need to wait for my entire logs to load? I could just basically just start loading the first few logs, show that immediately within less than a second, and even if the rest of the query on S3 takes 5 seconds, 10 seconds, I can just continue loading it below the screen. So we think this has got some very interesting ideas that we're experimenting with. And the catalog is going to be the key thing here. So we've played around with a couple of them. So one of them that I'm going to show a quick demo of if I have time, because I'm running out, is basically a node-based catalog where for trace data, we basically look at all the paths that the traces go through, and we reduce the fan out of that query to basically say for this operation in a GraphQL query, we know it only goes down these paths, and so we reduce the fan out significantly using this node graph-based catalog, which I can talk about offline if anyone wants to talk about it. But the key thing here is it has to be small, fit in memory locally, so we can quickly look up, the index. It has to grow sublinearly with data, and it has to significantly reduce fan-outs. The other one that we're looking at is trigram indexes, which MonarchDB made popular. That is a very efficient way of building a very cost-efficient index while also looking up fields and stuff like that. So anyway, this is a query. This is actually an early demo that I recorded before the event of how we're doing this with tracing. So we're starting with tracing because this is where we want to radically expand the amount of trace data that we're storing. So this is actually a 6-hour query. It's doing about 3 terabytes of data in total over that 6 hours, which is about 200,000 Parquet files. And using this graph-based catalog, we're able to filter it down by 3 to 6%. So it significantly reduces the fan out, and that's how we get it down to 1 second latency. And what we're actually doing with this, and it's a very fast demo, so apologies, it goes quite fast because I recorded it too short. But essentially what we're basically doing is we're doing trace-based kind of analysis. So we look at every single trace that matches that query, and then within a second, we're basically getting all the latencies, which services caused the most issues, where the errors, which spans had the most issues. So we're doing all that aggregation across a 6-hour window for all the traces in that period, and essentially bring it up, and this is all coming off S3. So now we're going to another one. So we're getting a lot of early evidence that this is possible. And this is something we want to build on, adding lambdas and a few other things on top of it. So, let's see. So, final thoughts. I guess this is kind of my call to action. So I've been in the industry as a vendor, now I'm at Netflix. We need to commoditize storage. Like I did a talk about 5 years ago on why not to build a time series database. It was the bane of my existence at my last company. Having to build, we went through 3 iterations of it, and it caused a lot of problems. And our engineering efforts didn't go into the end user features; they just went into building this time series database. And I think this is the problem that we're all struggling with. You know, nowadays we have better solutions like ClickHouse. I know a lot of startups are using that today. But at the end of the day, we need to commoditize storage the same way we've commoditized instrumentation using OpenTelemetry. And we want to see that come in, and we think the Observability Data Lake is the way to get to that commoditized storage. And the second thing that I'll just put, Chris is just at the front here. I hope you like the photo. Basically is, commoditizing storage is not just about being able to do low cost, low latency kind of storage. It's also about every time you migrate from one storage provider to another, at the moment you have to rewrite all your queries and all this kind of stuff because everyone has a different query language. So what we're actually trying to push with Chris's leadership in our team is essentially we've joined the CNCF Tag Observability Working Group, if you guys are interested, to basically come up with a query language that would be a standard for all the storage solutions out there. So we don't have to keep rewriting all alerts and dashboards every single time we try a new queries service. So I feel I've gone over my time, but that's it from me.
Awesome. Great work. We've got some time for some questions from the audience. We got here you go. A lot of roll.
I have a couple questions. First one is the demo that you just had. Is this using a house as a backend?
No.
Okay,
So is the demo you say you're using the
No,
cloud as backend?
this demo is only using custom code, querying Parquet on S3 with this catalog that I spoke about.
Got it. The second question is you mentioned about from the phase 1 to phase 2 you switched to the house, and I want to know what's during the migration and what's your thing that got you, and also you said you ingest about 1.5 petabyte today, and what's the cost saving in general? I don't think.
Okay.
So basically, like, what did you learn moving over to ClickHouse? Was that the?
Yeah. So ClickHouse radically simplified the architecture. Like we don't need the committers, we don't need the Druid clusters anymore, we don't need the PressDB clusters anymore. So we simplified a lot of the infrastructure just moving to ClickHouse. And again, we're still in that migration, by the way. So we still have some of that V1 and V2 kind of running in parallel. But with ClickHouse, it does a lot. I mean, there's a reason Uber uses it. We're now using it. You know, they're outside. You should definitely speak to them. You know, they provide a very performant, cost-effective way of handling large amounts of data. So that's why, you know, so in terms of cost reductions, it wasn't cost reductions per se in using ClickHouse, because if we, you know, the actual storage, you know, versus what we had previously was probably more expensive, because now we've got to run ClickHouse instances. But because we were able to reduce all the other infrastructure, get rid of the committers, get rid of the PressDB, get rid of, you know, the Druids, servers and stuff like that, and just simplify our architecture, that's where all the cost savings came from.
Okay, good. Thank you.
Mm-hmm.
Any other questions?
Okay. One of them.
Can you talk a bit about what problems you're trying to solve with NetFlow data? Like, why does that need?
What problems are you trying to solve with NetFlow
Oh,
data?
okay. So yeah, so we actually have a team that already does this, but they don't want to do it. They want us to do it because it's really hard to basically collect that amount of data and get analytics out of it. So, so the reason we do it is, you know, it's the typical things you do for NetFlow monitoring. Not all of our services are instrumented with tracing, so this gives you visibility into what else our service is connecting to. So that helps us with like dependencies and things like that. The other reason is security. Like, you know, so with NetFlow monitoring, you've got you're able to kind of see when you're getting DDoS attacks and see where they're coming from and things like that. It's very high cardinality data, and that's why this other team would like us to inherit it. But if we inherit it, we need to build this observability data lake so we can add another few petabytes of data over here.
Yeah, well, are VPC flow logs in the picture too, or is that not part of your?
Are VPC flow logs included too?
Not sure. I'd have to speak to that.
Okay.
Okay, there.
I respect that you can't share actual cost numbers, but I'm curious if you could give a ballpark number of engineers that are on the observability platform.
What's a ballpark number of engineers on
Well,
the
I said at the beginning of the talk, for our team, it's 9 engineers.
Okay.
So yeah, that's pretty much, for all this stuff, the data layer, it's like 9 engineers.
Thanks.
So, yeah. Okay. I don't know, it's quite a few. How about I take some questions offline after this and...
All right.
Yeah.
No, that's perfect.
Okay.
All right. Another round of applause. Thank you so much, David.
Thank you.